there, and it's, as I said, it is based, at least this part which I will show to you is based on the theory of generalized Toeplitz operator due to Fouché, Morel, and Gilman. So I got, so the main point is here that we can formalize everything in terms of Q. Q was this S1 bundle. So we had the manifold N, and we had this Q. Q was the bundle of lambda, or the total space of the dual bundle of the quantum line bundle, such that we had here K lambda, K lambda lambda is equal to 1. And inside there was not really inside, and in the interior in some sense, there was then the disk bundle, so the D, where the condition was here K lambda lambda was smaller than 1. And the main object was now here the Sensor projector, which gives a projection down to the space of, we have the L2 space, Q, with respect to this measure mu, which I don't recall, with respect to this generalized Hardy space H. These are those holomorphic functions on Q, which we could extend holomorphically to the interior. So arbitrary function on the boundary extendable to the interior. So I don't think that appears very good to read this, so we will come back to this. Anyhow, but what is important is the following, that why is this? Why we do this? We do this because we want to combine all the TFM which we have defined on the level of the sections to one global object, and this is exactly done by this global Toeplitz operator here. So TF. So the TF is important. The TF is an operator from H to H. It's again essentially done by the multiplication. So we have the function f downstairs on the manifold. So we put it back to our Q. This is this one. So we put it back to our Q. Okay, so we put it back. Here the multiplication. We put it back to our here it is. We put it back to our Q, and now then we multiply it, and then we leave again our subspace of holomorphically extendable function, but now we project it down again to this extendable function. And this is our global Toeplitz operator. And the important point was the following here, that we can decompose this global Toeplitz operator into modes with respect to the circle action. So the circle action, that's the rotation, and we can decompose it here, where this elements, these functions on U or on B, which are M homogeneous. So they are M homogeneous. This is the decomposition here. It's very important. I will not comment too much about this today. But let me repeat the basic fact. So we can identify this space HM. So these are the M homogeneous functions. You see M homogeneous functions, holomorphic M homogeneous function there on B. We can identify them with the holomorphic sections on the M tensor power of the bundle L. These are our primary object of interest. Okay. And we had an isomorph, we had a unitary isomorphy between them, and so with the scalar products compatibility. And indeed, it turns out that this TFM here, the TFM knows which work from here. We have the TFM going from TFM, the first one going from HM to HM. After identification of the HM in the holomorphic sections, we get that we can identify this TFM, these modes of this global operator, with the original Toeplitz operator, how we defined it the day before yesterday. So now I think I understand better why I said the quantum operator should not be considered an individual TFM. It should be the collection of TFM. Because from this point of view, you see that the quantum operator might be, it's better to consider this global Toeplitz operator as a quantum operator. And then what we will see indeed is that this TFM encodes also the classical limit. That's the point. Because the individual TFM does not encode the classical limit. We have to consider sequences or approximation. But the TFM encodes also the classical limit. So it is one way. It is the Toeplitz algebra is in some sense a non-commutative algebra, which is in some sense the quantization. Yeah. So it encodes the classical limit also there, but of course it is non-commutative in total. Yeah. Good. This is just to recall. Then I started with I wanted to show a certain part of this PMS theorem. This I did already yesterday. I will return in a more general context to this, so I just skip it for the moment, because the same thing will appear again. Now, the second part is, I think there is another thing coming into play, so this means that I repeat this, not repeat, that I do it, if I did not do yesterday. So, just as a little training how to work with Toeplitz operators again, you see these are, the Toeplitz operator are the global or even generalized Toeplitz operators in the sense of Boutet-de-Morel and Gilman. Where I said we will deal with two kinds of this. One is the TF, which is of order 0, and the other one is the rotation operator. The rotation operator, this operator DF, okay. This is a D phi, sorry, D phi, okay, good. So this is the rotation operator. So the TF is operator of degree 0, and this, the DF, is operator of degree 1. So this, if you know this theory of a two differential operator, you see it's a differential. You differentiate one, so it's degree 1. So degree 0 means it's a multiplication operator. And let's say a negative degree corresponds in our case in some sense to integration, okay? So this is the general philosophy there. But now let us look at a commutator. The commutator, this is for, you see, the terms are like for two differential operator. We have TF times TG minus TG times TF. So we have TF. TG minus TG times TF. Okay? Good. So, formally, you see, formally means that if we have an operator of degree k times operator of degree L, the product will be operator of degree k times L, and also the sum respects this. So this is degree 0, 0, so the product is 0, 0, 0, product is 0. So this is, from this formula, from this consideration, this is just a degree 0, okay? But, what's about its symbol? We did it, this is the previous slide, or the two previous slides, this we did before. The symbol of df times dg, that was f times g, or maybe the pullback of f times g, okay? Here, the symbol is g times f, the pullback of g times f. So, but the g's are, they commute. So the symbol is 0. So this means the bracket, this is a general fact, so it's not just what we here, but it's a general fact. The bracket of these two operators will be a Toeplitz operator, not of degree 0, it will be of degree -1. We go down by 1. Okay? So it's degree -1. And now we consider the following Toeplitz operator. Here, the generalized Toeplitz operator. I'm sorry that now we have the individual Toeplitz operator on the section picture. We have the this Toeplitz operator, let's say now the TF on this Q level, and this is the global Toeplitz operator, but the whole theory of Toeplitz operator, this is a theory of generalized Toeplitz operator of all level, which let me repeat it, it was just, we have that they are squeezed, they are just two different operators on, for Q, squeezed into these projections, okay? These are the generalized Toeplitz operator. And so, this will be a generalized Toeplitz operator, every combination here, because this is a ring. And now I make this kind of combination, or why I do this, because I want to show that this bracket asymptotically corresponds to the Toeplitz operator of the Poisson bracket. Now the normal Toeplitz operator is Poisson bracket. Hence I make this combination. So the point is, so here we have -1. This is now then this is -1, and this is 0. This is 1, so it's 0. This one is -1, but this is now 2. So we have formula. This is an operator of order 1. So if you just do it just like this here, and now we want to calculate its symbol. The idea is that it's in fact of order 0. So that means that the order will drop. The order will drop if and only if, for this iteration, if the symbol will vanish, then the order will drop. So we have to calculate the symbol. Now this is now the point. This is the point why I especially want to clearly this. So we have to do, you see the symbol, this is two differential operator calculus. The symbol of a bracket, that's equal to, we take now the Poisson bracket of the individual symbols, okay? This is the Poisson bracket, is now, you see this is the Poisson bracket there, on the P star Q, restricted now because the symbol makes only sense on the symplectic cone, sigma. Restricted to this here. So much, this is just to the differential operator calculus. Now the question is, now we want to express this are not yet our Poisson bracket. This is the restriction of the canonical symplectic structure to the symplectic code. Now in the next step, but this is some calculation which I will not show here, that indeed, that by the quantum condition, this quantization condition relating now our symplectic cone. This was the symplectic cone. This was a T and mu lambda. Okay, maybe we should not call it lambda. And you no, it's lambda. That's correct. Lambda from 2. That's correct. So this was our symplectic cone. This was for our contact form. It was given in terms of d minus d bar, our alpha. And this one was given in terms of our omega. So this was okay. Maybe I should say I cannot divide it. It was now d bar of my k. This is much better to call it k. This was the k. This was the metric. You see, this was the metric in the bundle. And the metric in the bundle is related to the metric on the manifold via the quantization condition. Recall that we have this relation d bar k is equal to the omega, so roughly with some factors and maybe some other things there also. So here you see the definition of this symplectic cone. This is the definition of symplectic cone is given in terms of our k, and our k is related to our omega downstairs. Okay, and now a more detailed calculation shows that indeed it is equal to our symplectic structure on M. Now this is our symplectic structure on M. This is the symplectic structure we have to deal with. It's not the symplectic structure on T star Q. It's the canonical symplectic structure. But there is a T coming into the play. So the T minus 1. So the point is that now if we calculate here now now if we calculate the symbol there, we have here, well, we have now t squared. So we have, I will not do it here, but nevertheless, so t squared, coming from the t squared symbol. We have 1 over t, and we have now the bracket FGN. Here we have a t, and also the bracket FG, the bracket O in N. Okay? So, so indeed we get that the symbol will vanish. So if we sit down and do it directly, and taking care of all these I and T's and so on. So in fact, our A is an operator of degree 0. So it is. So it is not not an operator of order 1. It's of degree 0. Hence, it is bounded. So it is bounded. Also, of course, one can say that it's a S1 invariant, but this is all of them is S1 invariant. So it is and then as before, meaning now the previous part of the proof which I had shown yesterday, we can now calculate the AM. AM is its mode. So A restricted to HM. So as we know, the T has eigenvalue M on HM, so we have M squared, we have now M squared, and now we have the bracket, because this T, which we TF with this global operator, if we split it to HM, we get a TFM, where the TFM are these individual modes there. So we have the bracket there, and now we have again M, and now we have this bracket, the Toeplitz operator, so now FG. So strictly speaking, we have the end mode of the global Toeplitz operator corresponding to the cross operator. Good. And now, again, A is bounded, so we can bound the AM by the norm of A. So bounding, so we have here this expression is bounded by the norm of A. And as yesterday, let me maybe just go back, just to what is our argument as yesterday. Okay, I did not also do it much more in detail here. I can divide now by 1 over M. I get now this expression which I wanted to have. So these are what is written there are, strictly speaking, for the proof for the modes of the global Toeplitz operator. But as we know that the global Toeplitz operator can be unitarily identified with the fifth Toeplitz operator which we want to have. So this is a statement about what we want to have. So the original proof of part A of this theorem there, that part A means that the limit of the operator norm of the Toeplitz operator goes to the subnorm of the function. So it is in particular to show that it's a non-trivial theory, because when we can form that theories which are trivial, okay, good, and then everything is okay. But it's a non-trivial theory, so we get really something. But I have to admit that our original proof was quite complicated and different. Well, so what we used there, we used Fourier integral operators, and in some sense we used them in some sense coherent states, but in disguise. So, but later with Alexander Karl-Reghoff, I was able to. I had a conjecture how to prove it better, and I was. But it depended on asymptotic expansion of the Berezin transform, and together with Alexander Karl-Reghoff, I could show this asymptotic expansion of Berezin transform. And this will be easy consequence, and I hope I will be able tomorrow to show you this very simple proof, okay? So in particular, I have to say that of course the coherent states are implicitly there also involved, but it's not so clear. We talk about distribution, heavy distribution, and such kind of thing. But for the Berezin transform, one also uses coherent states. I will introduce them either today or tomorrow, okay? Now, there was the existing proof of Starbuck follows now the same method here as before. First I wanted just to drop this, but then I decided maybe I should at least give you this kind of formula to say, just to show you how with this method the coefficients are determined. So the point is that you see, we consider our Toeplitz operators, generalized Toeplitz operators, generalized form of such a form here. So we have now Tf times T, because what is the idea? Idea was, in some sense, to have Tf times Tg, some kind of asymptotic expansion. So this here we have something like f. This is the idea, okay? Good. And so in this way we want to do it recursively. We recursively construct such kind of thing. We approximate Tf times Tg. Now, this is now something of order n, big N. So we go up, and we want to approximate it so that we have all of this what is above to be 0. Okay, so just we fix such coefficients here. Now we do it inductively. That we construct inductively a sequence of Cj such that this An is always a Toeplitz operator of order 0. Inductively we need something to start with, but this we start with the fact which we had already shown that the Tf times Tg, so minus Tf times G is a Toeplitz operator of order 0. Okay, this is our starting. So, and now I only have to show you how we do it now for the induction step. So first, this An is S1 invariant. This S1 invariant. Okay. So it is of order 0. This is by the induction. So the case this is how we do it. So, but by the S1 invariant, so really first. It is of order 0. This means it's simple. It's a function on Q. It's a function on Q because of order 0. The symbol is a function on Q. By the S1 invariance, you see we have the S1 action. So this means that this function, this is S1 invariant. This means that here we have S1 action. So this means it is a full deck of a function of M. So to say that indeed it is given by a full deck of a function on M. And now we take this function as the next element Cn fg in the star product. You see here we have only defined up to order n minus 1. Cn minus 1 is the biggest one. Now we have found a Cn. And now if we take an minus Tcn is of order minus 1. Of order minus 1, of course we did in such a way, and now the next step, An plus 1 is now d phi An minus Tcn fg is of order 0, and induction can continue. You see by this process that if one would ask, maybe calculate the coefficients, then you would run into trouble. Because at a certain step, at a certain stage, this is not really this is, first it's all recursively, but it's even not really very much constructive, because we say, we just know it is a Bulldagable function, but we cannot really say exactly what. So there is still the goal, or there is still the need, maybe to find some other ways to calculate this coefficient, if one is really interested in calculating this. As a mathematician, I'm not always sure when the physicists say, but we need to calculate figures and numbers. But they calculate, they have a huge paper where they calculate numbers, but what do they do with them? Nothing. It's nothing. It is, of course, the physicists sometimes they have the idea that they can get some of how it behaves by having a look on the number. Yes, okay, that's true, but sometimes it's much better to get an idea how it behaves by getting some structure, not just only the numbers. Okay. I'm not trying to offend you if you are a physicist, if you are really liking in calculations. Okay, good. Anyhow, they made the last remark on this with this aspect. The uniqueness, I said, because in the statement it says the star product is unique. And this comes from the part A. So because the part A says that we have in the limit we have the T F M goes to the subnorm of F. So this means they need only a unique star product. If there is one, but there is one, this is the shown. Okay, good. Now, the second theorem I will come back later. We will see how far I will get, but not today. As I said, these are now other techniques. Bergman transform, Bergman kernel, Berezin transform. But for this, I have first to study another object. And this other object is my friend Tarek Ali will like it. It's all coherent states. Okay, good. Okay, good. I don't know whether he likes this form of coherent states, but we will see. Or coherent states and coherent vectors, so it's the. These are the Berezin's coherent vectors and coherent states in the how it was generalized to bundles by Rawnsley. So sometimes these are called Berezin-Rawnsley coherent states. So coherent states for Berezin were related to functions, but here we have to be with bundles. I also have to say that we being Alexander Caravega and myself, we made a slight change, but this was just a minor change. So it's this is how I present it here. Is not exactly the original Rawnsley approach. So anyhow, this formula we had already. So we used it to identify functions on Q, to identify this with sections of the bundle. Okay. Now so the way was like this. You see, we have a section. We had a section there. And now the alpha, our alpha was an element from here. Alpha was from here. Okay, here it's written also. So alpha, where I even allow here, I even allow that it's from the total space of U. I have to exclude 0. So we had now, previously we had our S fixed, and now we got a function. Now we do it differently. We fix our alpha. So maybe I should have a bit more space here. So we have our total space U, and here the alpha is from the total space without the 0 section. So we have our manifold N. So and this we fix. And our current vectors, or later states, they will now, you see the current, I should say the current vectors will depend on the alpha. For each alpha we will obtain a covariant vector. So how do we do this? So first we have here our tau alpha. Here we project it down. This was our universal tau. So I don't have a vector. So first we project it down. Now we take this a section. This is the function. I just repeat again how the function was, how this object was defined. Now we take a section S. The S goes to the total space of Lm. So this is the S. So we get an element from the total space, and then we pair it with the alpha to the power m. This S goes to Lm, so that this gives now really a pairing. So indeed what we get in the following way is now a linear form. This is now this new interpretation. We get a linear form on the space of section. This is a linear form on the space of section if we fix the alpha. Okay? So it is linear in S. So with respect to alpha, it's not linear. It's M homogeneous, okay? But here it is linear in S. So now the point is that this is here in this case it is finite dimensional anyhow, so it is just linear algebra, usually linear algebra. We have a linear form on the space of global sections, which is finite dimensional. Hence, we can and we have a scalar product. This is our scalar product, which we have there. Hence, we can evaluate it. We can assign to it a vector, which just gives this by the taking the scalar product gives this linear form. So and this vector is called E alpha m. So E alpha m, that's a section in that E alpha m, that's a section of the space of that's a holomorphic section of Lm. So it will depend on the alpha. So because we have the fixed alpha, it will depend on the alpha. And we have this relation here. This is just this. And you see, this works also in the non-compact case by Rie's theorem. We have to have this continuous linear form, and then we get the same thing. So this is called coherent vector of level m. Now we check the following. So if you plug in, so what happens if I take c times alpha? So if I take the alpha, and I have now, you see, I have x here, and now I want to parameterize the things over our momentum space m. I want to, or let's call it vector, or there's objects there. I want to do it over m. So I have an x here. I have to choose first an element in the total space U above it. So we have now the alpha. We have alpha, or we have C alpha. C of course should be different from 0. This is our requirement, and we should check whether maybe this stays invariant. It will not stay invariant if you go to the definition. But it will not be completely arbitrary what we obtain. It will like this, that we have now the C, the conjugate of C, to the power m in front of this. There's a rescaling, so rescale this idea. The point is, of course, this has a little bit to do partly with conventions about where, if you have a scalar product, which one is holomorphic, which is the linear, which is antilinear. Here in my notation, I think I consistently try to use the definition. The scalar product will be antilinear in the first argument, which is the physicist's convention. Okay, good. This is there. So this is the first step would say, okay, the coherent vectors are not well defined on M. This is true, but we should not give up, okay, because what we obtain. So we obtain that if we consider not just the vector, but its projective class. So this is the projective class. So if we identify the vectors which are just only a constant time, non-zero constant time, we get a unique element. So that this means that is not a coherent state of the element. For this coherent state we can associate to X, and this is now well defined. Yeah?
Can you please go to the previous slide and say a few words about the pairing that you mentioned between?
Okay. Okay. Good. Of course, I did not repeat what was our setup. We have omega, we have HM, and we have maybe I should also have put an M here. Okay. This is our scalar product on the space of sections there, which is defined so with the help of this H. So we have integral M HM omega. So this was a little measure. This was our scalar product up to some maybe factor there, which 1 over n factorial and stuff, and so which is not important for us. Okay, but this was the scalar product. And so the point is that, so the argument is the following. This is linear algebra, okay, good. So linear algebra is that if we have a Euclidean vector space, or maybe here should not say linear emission vector space. This is a complex query. If we have an emission vector space, and if we have a linear form, then we can write this Hermitian form as a scalar, and we can find a vector. This is our linear form. Okay, this is our linear form. And now this is a fancy name, Rees theorem, but as this is 5-dimensional, it's not really necessary. We can say, okay, this is we can find a vector such that this linear form can be given by taking the scalar product of this. You see, this linear form is a function in S. Okay, this is very function. We do the S varying. So this is the S which we vary. So S here. Okay, and there is one vector. This is important. There is one vector such that we have this relation for all S. This is maybe the point, so which you might be asking. So there is one vector E alpha M, which does it for all S. Okay. Of course, if I write now down some kind of orthonormal basis in this space, I could give it explicitly, but this is not of help here in this context. Okay, good. Now we have the current state. The current state is now indeed well defined on the base manifold N. And indeed we could even do say the following. We could discuss current state embedding in the way that we take the M, and we take now the M. This is now our X. We take the corresponding vector from this projective space, and this embeds our M into this projective space. This projective space is of course one, but they of certain dimensions. So this is, we have the dimension of this space of holomorphic sections there, and we have to take this dimension -1, and this is the projective space. And this is what is called the coherent state embedding. The coherent state embedding, this is an anti-holomorphic embedding. So it is not holomorphic embedded, but we can conjugate it and we get a holomorphic embedding. And then we get, you see, this is what is there. This corresponds also to Kodaira embedding of Kodaira embedding type. But it is embedding, embedding with respect to special bases. It's not arbitrary basis, it's special basis. Good. So much for coherent state. Next step, covariant Berezin symbols. So with this already, I should say, it already appeared in the lecture course of English. But of course, in his context, this is this homogeneous subset context of C(n). So things are much simpler in a certain sense, or much or more complicated. More complicated in the sense that things are not finite dimensional, but simpler in the sense that you can write down everything in terms of functions. Okay, good. So again, we have to talk here about this vector bundle stuff and so on. So now we take an operator A. A symbol is always something you assign to an operator a function. This is a symbol. Some kind of, so we have now an operator A. In some sense, you see, quantization says, okay, we want to assign to a function an operator. So it is in this sense some kind of dequantization. So we have an operator, we want to assign to it a symbol, and maybe by studying the symbol, we will obtain some information about the operator. That's the idea why we do it. It's not because we want to be busy, but it's not a point here. So we have here an operator. Operator means in this sense, it is an operator from this holomorphic space to itself here. So A and so on. And now the covariant Berezin symbol is defined in the following way. So we have this coherent state E alpha M. The symbol is of course should be a function on M. So we have the X. And now this is defined in terms of the coherent state. So what we do first, we choose an element which lies above this X. An arbitrary element above the X. With one exception, we don't want to choose 0, okay? Because we have to exclude. And now, what we do, we now do, sometimes we take the trace there. But when we first write it like this, we have the scalar product, we have M, and then A E alpha M. This is the important part. But as if you check this, you will find out that, okay, this is not really independent of the choice. Then you renormalize the thing to make it independent of the choice of alpha. You take the scalar product of the first. In fact, there may be, from a more conceptual point of view, we can also formulate it like this. We have the so-called coherent projectors. The coherent projectors, they project, you see that we have this X and the alpha line above it, so they project things on the subspace, on the one-dimensional subspace in this column of this the section space, which is generated by the coherent vector, okay? So this is the coherent projector. And we can then write it as the trace of the coherent projector, and then after this the E. This is the Berezin symbol, covariant Berezin symbol. So also the notion of a covariant symbol exists. I will see whether tomorrow I have enough time. I'm trying to make it at least possible that I can do something about it. I will introduce it also. They are operated and presented as a certain integer against the coherent projectors. And for us, and now for maybe you could keep in mind, for Toeplitz operated here, fundamental symbol is F itself. Not the This is okay. As been a discussion in the morning here. So this means that by this I indicate already that there might be more than this one, and in fact it is the case. We could even give, by the help of certain things, we could even say this is how the ambiguity is like here. But for the moment, let us skip this and return to this maybe tomorrow. And now come to the Berezin transform. The Berezin transform again appeared also in Mirrek's talk also, but again here you see it is a statement about compact quantizable Kähler manifold, okay, which is in some sense just opposite to this what he presented here. We have the huge field of Kähler manifolds, and there are certain parts there, the compact case and the non-compact case, and even this is not the whole truth, okay? So this is the compact quantizable case here. The point is, this is so it is totally simple in some sense. So we start with F. We start with F. F is the function on M. It is just this other face case. And next we construct our Toeplitz operator of level M. Okay? Then we go back to the functions by considering this covariant symbol of this here. And this, the composition of, you see, this is again a function here. We start with a function and end with a function. And this is what we call the Berezin transform of level M. So we do it for all M also here. So the point is that why a different reason why it is quite interesting and helpful is the following. You see, now we are considering, you see, if we consider, we have F, E, M, F. We will also, I will show the next slide, I will show approximation results. But now, or asymptotic expansion results, okay? But now the situation is different, because in the TFM case, this asymptotic expansion stuff this could not be directly, in some sense, done to say, okay, let's take asymptotic expansion, because these are very different spaces. Here, this is always the same space. You see, we have the C infinities, it goes to C infinity. It's always the same space. We have a family of operators, and we can really study what happens, is there asymptotic expansion of this family of operators. Okay? And this is now this theorem. So, now, okay, maybe I should have tried to get rid a little bit of some of the words here, just not to overload this, but okay, this is now the complete formulation here. So, the statement is the following, that indeed, this IMF, so has, with respect to a given x, I fix an x on the manifold, okay? And then I study asymptotic expansion. Then the statement, sorry, then I have the statement here that this has now a complete asymptotic expansion in powers of 1 over m as m goes to infinity. So and this can be written, so it can be written asymptotically as an infinite sum here, where I have here now these are linear forms on the functions. Linear maps on the function, so again, function to function, and then evaluated at x. And with the following property there, that this II, as I said, are now maps. In fact, these are differential operators. These are maps, so that I0, the highest term, is just the identity. So the next term is the Laplacian here. Where the Laplacian is then has to be taken with respect to the metric given by the Kähler form omega. You see, we have the Kähler form, we have the metric, we have to take this with this. Then, what complete asymptotic expansion means that we can we have this sequence, and we can approximate this in a Fourier manner for A divided by m over r. So this means this complete asymptotic expansion. Okay, good. The starting point of this proof is there is the Berezin kernel Bm alpha beta, which I have already at least a symbol written down. So this, if I now, the point is, you see, I have the Bergman kernel. The Bergman kernel, this is the projector. This is the kernel function of the projector. Okay? Because we have this Bergman projector. This is the kernel function there. And now we have now so this would be from here to here, and then we have go one step further. And then one step further, we have 2 times the Bergman kernel involved here. So, and this, of course, one has to show something. It is not not directly obvious, but okay. If you are interested, we can check this in at least also in this reviews there, which I have written here. But in fact, this is very important, or also very important. That's a very important number. The Bergman kernel can be given in terms of covariant vectors. You see, the Bergman kernel, you see, this is a kernel function which is defined on U. So there is no need for covariant states. We can take the vectors. And now we take just the alpha and beta that correspond to 2 points above, x and y. And now we can show that this the scalar product of 2 covariant vectors, this gives the Bergman kernel. So Bergman kernel covariant states or covariant vectors are in some sense the same business. Also in the compact Kähler manifold. This is of course nothing. Nothing new in this CN open CN there, where everything is only in terms of function. But it's something which is really something new for this geometric situation with the bundles. Okay, good. Now I said I want to show, and let me show how this is useful to give a very simple proof of this first part. The first part, a little bit refined. This is a norm of the Toeplitz operator norm with respect to the scalar product. So don't forget, this scalar product is always there somewhere. So we should. So if we change this, it will change also things there. So and it's bounded from above by the subnorm. But it's also there is a c. The c depends on the function f. C, and it's also bounded from below, also by infinity, minus a certain constant, which is then 1 over m pi. So if m goes to infinity, then of course we get the equality. There is a first statement. In the first statement, this is what is more or less obvious, or let's say obvious here. You see, because and I think this also was used, this kind of argument was also used by Dirk. In this context there, the Toeplitz operator is projection times multiplication. And you see, now we have the multiplication. Here, this is the subnorm, and so this is of course bounded by the sub, the multiplication. And the projection is also, the projection is also non-contracting, so we have this relation there, okay? The second relation now, you see, this is now this is the covariant Berezin symbol here of the operator. So in some sense, here if we check this here, then by Cauchy-Schwarz inequality, we get the norm of this. You see the norm of this here. In terms can be squared. We revise the definition of this covariant symbol there. This is the definition of covariant symbol, and then by Cauchy-Schwarz we obtain this relation there, and then this is of course then bounded. You see here bounded by TFN. So okay, just Cauchy-Schwarz, just numeration. Now. So this was sorry, I have this I skipped because this is more or less trivial, more or less. Good. Now we take a point xe, a point where our f takes its maximum. Or maybe it's absolute maximum, okay? We have a point xe. By compactness, this is okay, so we can have such a thing. And now we take the asymptotic expansion of the Berezin transform with respect to this point xe. You see, in the formulation, you see, with respect to a point on the manifold, we have such an asymptotic expansion here. So where these elements have to say this EIM does not depend on the point. It's only that this approximation depends. How fast it approximates will depend on the point. So we have this relation there. So this is we take fxe and we take the asymptotic expansion of the Berezin transform IMF, and so this is now bounded by C over M with a constant C. So this is the existence of this asymptotic expansion. Okay, good. So now we can of course then say, okay, how we're going to interpret this. So if this is also linear algebra, it is in the second form of triangle inequality. So we want to dominate. Now I have to take absolute of this minus absolute of this. It's dominated by C over M. Okay, good. And now let us see. So this says that f sub minus em is fxe minus em. This is less than this here. What is written here? Okay, xe, and this is less than the norm of IMF. And now this gives the statement. So this gives the statement that we have now. You see, this one is a lower bound for our TFM. Okay, good. I think think I still have very few minutes. Yeah, okay, very good. Because now I want to introduce here a way for the Berezin star product. So we can use it using covariant symbols. We can use another star product, which is called Berezin star product. But let me already put in the very, very beginning under very restrictive conditions on the manifold. So, for example, in this homogeneous business, which was presented by you again, it works. Okay, but in general, for compact Taylor manifold only if for certain compact homogeneous spaces. Good. So we will find another method to construct another star product, which we call the Berezin star product, in another way. But this is then for the moment. Today. So we have, you see, this is our C infinity M. And now we have a certain subspace of level M covariant symbols. Yeah? We take all operators and we take all its covariant symbols. This is a subspace of the subspace of all these functions there, because the symbols are nothing else as functions. Now, the symbol map, this covariant symbol map, so this was the sigma, also A to sigma MA. This was the covariant symbol map. This covariant symbol map, this is injective. This follows from the fact that the Toeplitz map is surjective. I hope, maybe if I have time, I will show this tomorrow. So now this has the following consequence. If I take now two symbols, okay, meaning if I have sigma MA and sigma MB, two symbols there, meaning that they all appear as by this symbol map. And now the statement by this one, that injectivity means that the A and B are uniquely fixed by it. So we have only one A and one B to these two different functions. Now we said the following. So this A and B is fixed. Now we said the star product of level M of these two functions, which are symbols, is nothing, we take just to be the symbol of the product of these two operators. This is now a product on the space of symbols. Okay, it's not a product of symbols, it's a space of symbols. But from this definition, it turns out that this star M is associative, and of course it's commutative. So associative, popular. The crucial problem, so we want to have a star product on C infinity M. And now we have a family of star products on these subspaces there. The question is, of course, maybe this defines the star product in C infinity M in a certain way. And meaning that in particular the star product for all functions should be independent from the level M. Even if maybe not all functions will be quantized, okay, this is something which we have to deal with, which we deal also in other contexts. But the main point is this, independent of the level M. And in fact, it turns out that this in general is not possible, only for limited classes of manifolds. And the crucial fact will be made by something which is called Berezin's epsilon function. If the epsilon function is constant, it will work. If not, it will not work. And in general, it is not constant. And this is in terms of the approach, which was done not only this traditional Berezin, but then later it was approached, was the way done by Kahn-Gut and Ronsley, who analyzed the situation in very detail. And the main point is, in some sense, what they used is for their construction then is they embedded these sections in one into each other, so level M and right. So but this cannot be done in a coherent way. That's the problem, in a natural way. And this is the reason why it fails in German. Okay, thank you very much. So this is so much for the debate.